So hey guys, I'm back. Today I'm doing the final video from from my trip to Fermilab. This video is going to be just about Tevatron, their particle accelerator that got shut down last August. So I already did a video on the accelerator chain, which feeds Tevatron, so I'm not going to start talk about that. But so I'll get started. Tevatron is was the highest energy particle accelerator in the world until the LHC came online, and it stopped operation in August 2011. So it is no longer running due to funding, the loss of funding, which is really sad. But it was running at a center of mass energy, which is basically collision energy, of about 1.96 TeV. So they never actually fully got 1 TeV per beam. The name Tevatron comes from 1 TeV beam energy. They never actually got 1 TeV full beam energy. They got like 0.99 or not 0.99, 0.9. So their center of mass energy was not fully 2 TeV. It was very close though. So for, only nitpicking would you really say that it wasn't 2 TeV or center of mass energy. So Tevatron is about 4 miles in circumference. It's fully on Fermilab property. In the center of the Tevatron ring is a nature preserve. You can't go in it. It's like a swamp area, nature preserve for animals, because Fermilab is very into nature and conserving the environment. So that's the center of Tevatron, but let's get on to the science. So Tevatron is fed by the main injector / recycler, which are 2 rings in one tunnel. The protons come out of the main injector into Tevatron, and the antiprotons come out of the recycler into Tevatron, where they're accelerated to their beam energy of 0.9 TeV. So Tevatron uses superconducting magnets, as you can see in this picture, superconducting magnets to bend the beam. What was before Tevatron was called the main ring. So before they had Tevatron, they had the main ring, which used room temperature magnets. And as you can see from this picture, around the whole ring of Tevatron is actually like water. It's like a sort of a slow-flowing river all the way. The water gets pumped all the way around, and this was to cool the old room temperature magnets that were used in the original Tevatron, which was called the main ring. When they upgraded it to Tevatron, the superconducting magnets doubled the beam energy, because basically what constrains beam energy in particle accelerators is not the amount of energy. They could accelerate beams much higher than the 4 TeV they're doing now per beam in the LHC. The only issue is their magnets aren't strong enough to bend such an energetic beam. So really, the thing that is stopping the beams from being higher energy in particle accelerators is the magnet's bending strength, because the magnets can only bend a beam of a specific energy. So in order to increase the energy of the main ring, they had to increase the energy of the magnets. So they went from room temperature magnets to superconducting magnets, which means there's no losses in resistance due to the magnets, so you can put more current in them. The only thing with superconducting is it isn't perfect, and if you put too much current in, the superconductor will stop being a superconductor. So Fermilab's magnets, as you can see, this picture isn't actually the real beam line for Tevatron, but is a mock-up of Tevatron on the 15th floor of the Wilson Hall building, the main office building at Fermilab. So the room temperature magnets are placed, I think, on the bottom, and the superconducting are on the top, but I could get those reversed. In any way, it doesn't matter. So they just put the superconducting magnets over under the room temperature magnets just so to be economical and save space. But it's interesting that the room temperature magnets were actually cooled by the water above. So Tevatron was actually originally called the energy doubler. It was the energy doubler upgrade to the main ring, because it would be able to double the energy. In fact, from I think like a few hundred GeV to like 500 GeV or 600 GeV maybe, but they actually kept increasing the energy until they got almost up to 1 TeV per beam, which is much higher than they anticipated, but that was all because of the superconducting magnets. So Tevatron works in a very similar fashion to the LHC, with the RF cavities to accelerate the beam, and the magnets to contain the beam in the circle, and dipole magnets, to contain the beam in the circle, and quadrupole magnets to actually focus the beam. but they also have sextuple magnets. And so if you think as a particle goes into a magnet, right? The particle, since protons are going to be in bunches together, protons repel each other because they have the same charge. So between the time they go from one magnet to the other, which is a very short time, but it's enough that the protons will have separated a bit. So they're going to move between each magnet. They're going to move apart. And then they hit the magnet, and they're either, if it's a quadrupole, they're going to converge to either the x or the y-axis, or if it's a dipole, they're going to curve and not converge at all. They're just going to curve. So if you think about particles doing this, particles are oscillating back and forth all the time, because when they hit one, say there's an x quadrupole and then a y quadrupole. If a proton goes into the x quadrupole, it's going to get focused onto the x-axis, and then it goes into the y quadrupole, it's going to get focused on the y-axis. So it's going to be brought to the side and then to the center. So if you can think that proton is moving, so if you can think that there's like hundreds of quadrupoles on the Tevatron ring, so the particles are actually oscillating back and forth between the quadrupoles and the dipoles all the time. And you may have seen that they have occasional sextuple magnets in Tevatron and LHC and synchrotron devices like those. And the sextuple magnets are to control the oscillations. They have special words that I forget. They told me, but I forget them. But they can basically control the oscillation of the protons and the antiprotons. So they can control that. Basically, they can say every time the proton goes around, it'll be in the exact same oscillation. They can say every other time it goes around, it'll be in the same oscillation. Every third, every fourth time it goes around, it'll be in the same oscillation. And they can use sextuple magnets to actually control it, because the sextuple magnets can force it to the opposite side, or something like that, so that the protons will actually change their oscillation or keep the oscillation depending on what type of thing it is. So that would be used so that the beams would actually hit each other, because if you think about it, you want the beams to be as lined up as possible, because you're already not going to get very many collisions. So you want the beams to be lined up as possible, so they can basically, if you have the two beams oscillated to different polarities, while that distance in like micro nanometers may not be very much, it may be enough that the protons miss. So you want to control their oscillations so that they're both at about the same point when they hit in the two main detectors, which are CDF and D0. So Tevatron also has numerous access shafts, because the whole Tevatron accelerator is on Fermilab property. They're 5,200 acres of property. It's huge. But the whole accelerator is actually on Fermilab property, so there's numerous access sites every few hundred yards. So you really don't have to actually go far in the underground tunnel. So that's really nice. It's very convenient, but you're not allowed to be in the tunnel when they were running. I don't know why they didn't let me in the tunnel. I guess lack of time or something. But also running along the tunnel between the top of these access shafts is all the coolants. So you have the huge liquid nitrogen and liquid helium and a bit of liquid argon storage you can see here in these tanks, massive amounts. And this is sent around the ring to cool the superconducting magnets, and for the detectors use some of the liquid argon, I think. But also the ring, you may think like something like the LHC, 100 meters underground, very deep. Tevatron, not so much. It's only 30 feet. So in fact, the basement of the CDF building, as you can see here, the CDF detector was actually just rolled in right to the right of that. So really simple to get it. You didn't have to lower the thing down in massive segments. You just have to roll it in, because the whole Tevatron accelerator, it's pretty shallow actually, comparatively to something like the LHC or their neutrino experiment. It's only 30 feet underground. But I guess they've determined that shielding is adequate. But as you can see, over the actual beam, over the actual tunnel, they have placed a mound of earth just for added shielding. But I mean, if you think there's a concrete tunnel, so the shielding is pretty good, I would say. If you guys get a chance to do this, take whoever is giving you the chance, take them up on it, because I had a ton of fun. It was a really awesome opportunity to go to Fermilab, and the lab you go to doesn't have to be Fermilab. It can be any lab. There's lots of physics labs all over the country, all over the world, in fact. So even if you don't live in the U.S., find somebody, meet somebody, look online for tours, see if the lab is open to the public. Fermilab is even open to the public. You're not going to get to see what I saw, but you can certainly see something They have a little museum. You can drive around, see their buffalo. There's bike paths and stuff. And they do have tours of the accelerator stuff sometime. Okay, so this is the control room. I haven't really mentioned this in many videos, but I did spend a long time actually talking in the control room to their physicist there, one of their head physicists. But the control room has many computer stations which can be set up to control any aspect of the accelerator chain, including Tevatron. And theoretically, they said, any computer place, block of computers, workstation, whatever you call it, can control any aspect of the accelerator chain, any aspect of Tevatron, any aspect of the neutrino experiments. But they said certain things tend to stay at specific computers. They said that operating Tevatron in the control room was very crazy, because if you think about it, there's literally millions and billions of things that you have to get right for Tevatron to work. It's a very complex machine. So they said the control room would be crazy when Tevatron was running. And the thing is, you can't stop Tevatron overnight, because if you think about it, you have magnets, they got to stay cool. You have beams, they got to stay in, you got to ramp them up. It takes a long time for beams to ramp up energy, because you have to get, enough antiprotons. So they do have to run Tevatron 24/7. When it was running 24/7, except maybe holidays or technical shutdowns. So they would have people in there 24/7. You'd obviously have a smaller night crew to run Tevatron. You probably wouldn't be doing experiments in the night, although you could be. But you would have to keep people there to keep the beam running. And so this whole control room, as you can see, I didn't take pictures of this, so I'll try to find a picture online. If not, I apologize. You'll have to look at a blank screen. But what they have is they have a grid of wires. And one wire has high voltage on it, and one wire has ground. And the wires are separated so much that there's no sparking between them. When a particle actually passes through the wires, they'll get a current spike on that wire. And so they're measuring this in various places along the Tevatron beam line, and the rest of the accelerator beam line as well, the rest of the accelerator chain. And so they can actually see, based on this, when a proton, say, passes between the wires, when the bunch passes between the wires, it will cause a current to flow between the wires, and they can measure this current and they actually graph this on the computer, so you can see if the beam's hitting a wall. You're just going to get random lines and spikes on these graphs. They have X and Y graphs for each position, and you can see that they basically have their shape. Usually it's like a Gaussian shaped curve, although it doesn't always have to be, but they have their desired shape on the screen and the actual shape on the screen, and they manually will change the magnet strength so that it'll bend the particles to actually get all the way around the ring. So that's how they do that manually. Some of it's automatic, but it's mostly manual. So that's how they can actually steer the magnets, and so they can see if say the beam is hitting the wall, the beam's going to be all over the place by the time it gets steered by the magnets to the next sensing place, and so you'll just see everything. There'll be a very large curve. It won't be very steep, and all the bars will basically be at the same place, which says your beam is all over the tunnel, not focused on the center, or slightly off center focus, which I saw for some of the places. So that's how they'll actually focus the beam. But also in the control room, they have visual and auditory cues, just so you can quickly get an idea of whatever's going on. So I thought that was interesting, and I hope you understand at least and appreciate how well it is to actually manually steer everything with magnets, by manually changing the magnet strength using these graphs that are caused by high voltage X and Y wires that are placed right next to each other, and they can record the current going between them. But the CDF detector, the actual layering of the detector, is fascinating. It's on the inside. They have the pixel detectors, which are silicon-based detectors, and they can detect very precisely where particles are. They may not be able to identify them very well, but they can track very precisely the particles, and so they show paths of the particles very well because they can track precisely. And this whole detector is encased in a magnet or two, a very large magnet, and this is so that the particles will actually bend their paths as they go through the detector, so they can see whether it's a charged particle or not. Charged particles will bend, uncharged particles will not bend. So they can see that in the silica detector. Then after that, at least in the mock-up, they showed a gas detector, and the gas detector has much less. Basically, if you could give an analogy to a camera, the silicon detector would be like 10 megapixels, and a gas detector would be like 1. You have much lower density of the detectors, so they can detect less accurately the position of the particles. But they will use that because at that point the particles are going out from the collision. They're separating, right? If you think about it, like you hit a pool ball and it hits the triangle of balls, they'll separate as they get farther away. At the beginning, they're very close, and as they get farther away from and as they get farther away from the original collision point, they'll separate. So same thing with the particles. So you don't need as much density as you needed in the silicon detector. And then after that, they go into like various calorimeters or muon chambers or something. And calorimeters are used, basically a calorimeter will destroy the particles. So you really, you want to have calorimeters on the outside of your detector because they'll actually destroy the particle, but what they do is they destroy the particle and absorb its energy, so they can actually measure the energy. So the energy will be absorbed into something like steel or something, and they can get that energy, they can read that energy. And so that's how a calorimeter works, and it will give them information on the particle's energy. And using the particle's energy, they have already determined its location and its charge from the pixel detectors, what the silicon detectors right next to the actual collision point are called. So that's that. Fermilab has recently shown a few results on the Higgs boson, but they didn't really have enough energy. But they did discover the top quark. They've actually seen a top quark out not constrained to a baryon or a meson, which is top quark is the only quark that we've had proof that it has happened outside of a baryon. Or a meson, because the top quark decays so fast that the strong force can't act upon it to make a particle, but the strong force is fast enough to act on all the other quarks to form them into hadrons before they can decay. With the top quark, that doesn't happen, so Tevatron, actually, CDF and D0, saw a top quark outside of a hadron, which is awesome. It's really cool. So that's Tevatron.